In this video, we're going to talk about inductive and deductive reasoning. So first off, when several examples form a pattern and you assume the pattern will continue, you are applying inductive reasoning. Next, when a statement you believe to be true based on inductive reasoning is called a conjecture. So the word conjecture means the statement you believe that is true and it's based on inductive reasoning. A counterexample, we're going to use this quite often, shows that a conjecture is false. So we use it to explain or give an example that proves that a statement is false. So we need to find the next item in each pattern: March, May, July, blank. So if you notice, March is the 3rd month, May is the 5th month, July is the 7th, so we need the 9th month. So that would be September. Then next we have 1/3, 2/4, 3/5. So if you notice on top, they're increasing by 1, so that would be a 4 on top. At the bottom, they're also increasing by 1, so 3, 4, 5, so the next would be 6. But then reduced, we would end up putting really a 2/3 there instead, so remember you want to reduce it. For the last one with the little picture, we have going up and down, and then vertically, and then vertically, horizontal, then vertically. So we know it's going to go horizontal, but you have to notice how many you've got in each of them. So we have 1, there's 2, then there's 3, so we need to have 4 circles horizontally. This is where we're going to use the counterexample idea, and that is that we need to figure out if our statement is true or false. If it is false, we need to give an example of where it is false. So in this first one, when we talk about Kennedy as the youngest U.S. president to be inaugurated, so you first have to know that Kennedy was 43 when he started as a president, and he is not the youngest president. Teddy Roosevelt was actually the youngest, and he was 42 years old. So next, 3 points on a plane always form a triangle, and not necessarily, and that's why we want to show that it's false. In a situation, it would be false. Remember, you can draw a diagram for this as well. That if we have 3 points, the only way that they're not going to form a triangle is if they all are on the straight line. So the 3 points are collinear. For number 10, for any real number x, when we square it, that it's greater than 1, and when the x is just by itself, it is greater than a positive 1. So what we have to think of is when it's not going to be a 1 is when x is going to be a negative number. So if x equals -2, then when I square it for this first situation, it ends up getting a +4, which is greater than or equal to 1. So that part works, but the second part does not, because the x itself, -2, is not going to be greater than or equal to the 1. Number 19, every pair of supplementary angles includes one obtuse angle. So remember, supplementary means that they add up to be 180 degrees, but that does not mean that that one of them needs to be obtuse, because what happens if they're both right angles instead? That they still add up to be 180, but they're not obtuse. For these 4 questions, we need to make a conjecture about each pattern. We need to write the next 2 items. So for the first one, we can see it goes from 2, 4, and then 16. So if you notice, this one's a little bit trickier, but the way that we get the 4 is if we square the 2. The way we get the 16 is if we take the 4 and we square it. So that means that we're taking the previous number and we are squaring it to find the next term. So we're going to take 16 squared, and we end up with 256. So that's the next term in the sequence. And if we did that again then, so 256 squared then gives us 65,536. For number 22, you can see that it's going from negative, positive, negative, positive. So we know the next term will be a negative, and then the one after that will be a positive. But if you notice, it's counting up by 3. So 3, 6, 9, 12. Next would be 15, and the next would be 18. For number 4, we're looking at the picture itself, and if you notice that there's a bigger part up here on top and a smaller part. So if you notice, the bigger part switches to the bottom and it flips. So it's literally flipping around, but it's also rotating the other way at the same time. Then from this shape to the next one, it's flipping again, and then this one is rotating the same way again, and it starts all over again. So these are the next 2 pictures that would end up in our sequence. For number 31, the Fibonacci sequence is it takes the previous two numbers, previous two terms, and we add them together to get the following number in the sequence. So that would mean that I'm going to take the 13 plus 21 to get 34 as the next number in the sequence. The one after that, then I need to take the 21 plus the new number, my 34, to get 55. So 55 would be the second number in after this. We need to determine if the conjecture is true or false. If it is false, we are going to write the counter example. So for number 24, points x, y, and z are coplanar. That means that they share the same plane, and this is true. And that is because all it takes is any 3 points, and we can draw a plane through it. So all 3 of those points, if we have any 3 points, doesn't matter where they are in the figure, that they will be coplanar. For number 26, in a triangle with one right angle, 2 of the sides are congruent. Well, that's not always going to be true, so it's going to be false. And a picture could be, so remember it has to be a right angle. I know that a Pythagorean triple, so I know it's a right angle, is 3, 4, 5. So I'm going to use that as my counter example. So no, the sides do not have to be, the two sides, the two legs do not need to be congruent, so since we can see the 3 and the 4 are not. All right, so next we are following up with our deductive reasoning. So we're no longer using a pattern to determine what comes next. We are using facts, definitions, accepted properties, and the laws of logic to form a logical argument. And this is different from our inductive reasoning because that uses specific examples and patterns to form a conjecture. Go ahead and add this in just on the border or margin of your paper. So one little side note before we start talking about the law of detachment is there's different types of logic. So a conditional statement has 2 different parts, and it's just going to be a sentence, and it's kind of an if-then sentence. That's the biggest part. So the if tells us the hypothesis portion of the sentence, the then tells us the conclusion part of it. So for example, if I study hard, then I will pass class. So think of science class. The part that happens first is your hypothesis. Second, then, is the conclusion. So what's the result of what happens? So here, if I study hard, then I'm going to pass class. Then that's the conclusion. So I'm going to be mentioning conclusion and hypothesis in this next section, as well as some sentences. One form of deductive reasoning is called the law of detachment and law of syllogism. So for law of detachment, sorry if you can hear the lawnmower outside, is if we have the hypothesis of a true conditional statement, so you have to make sure that the statement itself is true. If the hypothesis is true, then the conclusion will also be true. The law of detachment is also called a direct argument. So the law of syllogism, also called the chain rule, and think of why it's called that, think of what a chain looks like, that it all connects together. The same thing will happen here. So if the hypothesis happens first, so here excuse me, I'm going to give you an example. So hold on one second. So for example, if it rains today, then we will get wet. If we get wet, then we will need to dry off. So the conclusion I can make then is I tie the very first to the very last. So if it rains today, then we will need to dry off. So here are 2 examples of the law of detachment, and we need to use it then to make a conclusion in the end about this true situation. So 2 segments have the same length and they are congruent. So if we are given that BC is the same length as XY, then we know that the conclusion then should be that they are congruent to each other. If you notice how I color-coded it as well, so if 2 segments have the same length, so if you see that part in purple, that means the same thing. So BC is the same length as XY, then we can say that they are congruent. So BC is congruent to segment XY. So next, Mary goes to the movies every Friday and Saturday night. Okay, so that's a true statement. We're assuming that that is true. Today is Friday. So the conclusion that we can make then is that Mary is going to the movies tonight. All right, so for this one, we need to, if possible, use a law of syllogism to write a new conditional statement that follows from the pair of true statements. So remember, the law of syllogism, that's the one that is the chain rule, so it connects everything together. So if Rick takes chemistry this year, then Jesse will be Rick's lab partner. If Jesse is Rick's lab partner, then Rick will get an A in chemistry. So if you notice, the middle parts are the same part over again, so that means we can tie together the beginning and the end. So our statement will be, if Rick takes chemistry this year, then Rick will get an A in chemistry. For this next one, if x squared is greater than 25, then x squared is greater than 20. Okay, so if x is greater than 5, then x squared is greater than 25. So one thing you want to notice is the parts that are the same. So really, this statement almost needs to be put kind of in a different spot. It needs to be up here at the top. So if we say if x is greater than 5, then x squared is greater than 25. If x squared is greater than 25, then x squared is going to be greater than 20. So that way, again, we can tie together the beginning and the end to make our statement. If x is greater than 5, then x squared is greater than 20. For this next one, if a polygon is regular, then all angles in the interior of the polygon are congruent. If a polygon is regular, then all of its sides are congruent. Okay, so one thing you have to notice is these are two separate statements, but there's nothing that's the same except this very first part of the sentence. So this is not set up as the chain rule or the law of syllogism, so we cannot write a new conditional statement that follows from the pair of true statements.